So, having looked at the evidence that the hippocampus is the change manager for the cortex, I'd like to describe the information models for change management processes that are performed by the hippocampal system on several levels of description. And we're going to start with what's happening at a high level of description, the level of cortical areas and columns. To focus our thinking, let's think about how the brain handles looking at a novel picture. And let's suppose that this picture, a penguin shooting out of the water to join another penguin on an ice ledge, let's suppose this picture is novel to the brain. To simplify things, we'll just consider activity in three cortical areas, each area made up of an array of columns. The top area detects receptive fields that can discriminate between different objects. The middle area discriminates between different types of groups of objects, like the jumping penguin and the water dragged up by the jump, the other penguin and the ice shelf he's standing on, the ocean along the bottom and the mass of ice. The bottom area discriminates between even more complex circumstances, groups of groups, if you like. Inputs from closer to visual inputs arrive in the top layer, outputs from that layer go to the middle layer, and outputs from the middle layer go to the bottom layer. So, when first looking at this picture, the pattern of receptive field detection might look a bit like this. There's quite a lot of receptive fields detected in the top area because I'm assuming that the objects, penguins, ice, ocean, are relatively familiar. But the juxtaposition of these objects in groups and in groups of groups is a lot less familiar. So there's rather fewer receptive field detections in the middle and the bottom areas. So there has to be receptive field expansion in those bottom two layers. Now let's suppose that each area needs an additional 2 detections to get to the minimum level. Because changes to receptive fields must be as small as possible, the degree of internal activity in a column is the primary indication a column is an appropriate change candidate, because once again, high activity in the middle layer shows that a relatively small change will be enough to tip it over to detection. So let's suppose that the columns coloured pink have a high degree of internal activity. The problem is that there are 3 good candidates in the middle area, and only 1 in the bottom area, but 2 are needed in each area. So how do you pick between candidates in the middle area and find more in the bottom area? Well, to find more, you can look at lower but still significant levels of internal activity, and I've coloured columns like that in pale pink. That adds a few. There are now 5 candidates in the middle area and 3 in the bottom. That's more than enough now, but how do you pick the best? Well, we need more information. Suppose that the group of columns indicated by the blue arrows have tended to expand their receptive fields at similar times in the past, and the group includes quite a lot of columns that are currently detecting their receptive fields. Suppose the purple arrows indicate another group that's often expanded their receptive fields at the same time, and again, there are quite a lot of currently active columns that belong to that group. This adds some relevant information. If 2 columns have the same degree of internal activity, but one of them has often expanded its receptive field in the past at the same time as quite a lot of the currently active columns, it's probably the better candidate. So in the middle area, 2 of the 3 columns with strong internal activity are also part of such groups, so they can be selected. And in the bottom area, the 1 column with strong internal activity can be selected, and one of the columns with moderate activity is a member of 2 groups that have often expanded receptive fields at the same time, so it's the best candidate for the 2nd column in the bottom layer. Receptive fields can then be driven in the 4 selected columns. So in summary, the selection of the best columns for receptive field expansion is achieved by a combination of internal activity and past expansions that were temporarily correlated with the currently active columns. And the hippocampal system has the structure to implement these criteria. Let's move to a deeper level of description. As we've discussed, the degree of activity in layers 2, 3 of a column is the primary indication that a column would be an appropriate candidate for receptive field expansion. Internal layer 2, 3 activity in columns across the cortex is transmitted to the input layers of columns in the perirhinal and parahippocampal cortices. Each group of cortical columns targets a different column in the perirhinal or parahippocampal cortex, where the cortical columns in one group have tended to expand their receptive fields at similar times. The diagram simplifies things a bit because any one cortical column could actually be part of more than one group. But what that connectivity means is that if there's strong internal activity in a perirhinal or parahippocampal column, it means that there's strong internal activity across a group of cortical columns in which there's been simultaneous receptive field expansion in the past. Internal activity of different groups of columns in the perirhinal and parahippocampal cortices target the input layer of the entorhinal cortex columns. So columns in the entorhinal cortex have receptive fields that are groups of groups, very large groups of columns from lots of different cortical areas that expanded their receptive fields at similar times in the past. Then, layer 2-3 activity in the entorhinal cortex columns is communicated to neurons in the hippocampus proper. Granule cells in the dentate gyrus, pyramidal neurons in CA1 and CA3. So these hippocampal neurons have receptive fields that are extremely large supergroups of cortical columns that have tended to expand their receptive fields at the same time in the past. And because the hippocampal neurons in the different regions get their inputs from the same source, there's going to be a degree of similarity between receptive fields in the different regions. Different neurons in the hippocampus correspond with different very large groups. But again, not illustrated is the fact that one column in the perirhinal, the parahippocampal, or the entorhinal cortex could be a member of many higher level groups. There's a competition process between different neurons in CA3 and the dentate gyrus, and this competition determines which very large groups of columns are the most appropriate for current receptive field expansion. These choices are communicated to the CA1 neurons with receptive fields corresponding with the selected groups. And the CA1 neuron produces outputs back to the output layers of the group of entorhinal cortex columns that form its receptive field, although actually this omits the role of the subiculum that's fitted in between the two structures. An entorhinal cortex column may be part of the receptive field of more than one CA1 pyramidal, and entorhinal columns that get inputs from a number of CA1 neurons will tend to produce an output, with receptive field expansions as necessary. So the entorhinal receptive fields are updated to reflect the current simultaneous receptive field expansions. An entorhinal cortex column output goes to the output layers of the perirhinal and parahippocampal columns that make up its receptive field. And again, one perirhinal or parahippocampal column may be part of the receptive field of multiple entorhinal columns. So the target columns that are part of the receptive fields of multiple active entorhinal columns will get the strongest inputs and will produce outputs, and again with receptive field expansions if required. Then the outputs of the parahippocampal and perirhinal columns go to the cortical columns that form their receptive fields, and cortical columns that get strong input, perhaps from multiple perirhinal and parahippocampal columns, will expand their receptive fields. So the organization of reciprocal connectivity between cortical columns and the hippocampal system selects the most appropriate columns for receptive field expansions. And it does this by a combination of the degree of internal activity and the degree of membership of groups of columns that expanded receptive fields at the same time in the past. Then, signals go back to drive expansions in the selected columns, and in the process the signals update the records of which columns expanded at the same time with information about the current expansion. So, this covers how information is collected and distributed. The next question is how the competitive selection process in the hippocampus proper works, and we'll cover that in the next section.